Okay, so here's what we were talking about last time. So a quick reminder of the big point from last time. We were talking about single variable calculus, and I wanted to make sure that we all go in with the right idea of, well, if we're going to define multivariable integrals, well, we really ought to base that definition on, well, what are single variable integrals? Right? You don't want to use the same word for completely different, unrelated things. So we have to have a clear idea in our mind of what are single variable integrals first, and my assertion is that single variable integrals are Riemann sums. That's most fundamentally, the definition of what a single variable integral is. And I went through and made a big case about how it had better be, because otherwise we can't use integrals to solve any applications. Right? All of these various different applications connect to Riemann sums. Area under the curve is just one of the many applications that connects to Riemann sums. You take out Riemann sums and the whole thing falls apart in terms of applications. Okay, all right, so make sure that you're good with all of that business, all that stuff you thought you were done with because you finished single variable calculus. It's back. Okay. Okay, so now let's summarize what happened here in this calculation, in this expression here. What's being done? I'm going to draw a picture up here. A couple of different applications. There are a couple of different ways to think about Riemann sums. You could be looking at like a rod along the x-axis there. Right? And so this is a solid rod where maybe the density is not constant. Maybe the density is sort of increasing as you move over toward the right. Right? Less density on the left, more density on the right. What's the mass of this rod? And so you can write down a single variable integral that answers that question. Here's another application, one that you're probably more familiar with. But suppose you have a graph of some function and you want to compute, let's say the area under the curve, for example. Right, everyone's most familiar application of integrals. So familiar people think it's a definition, but it isn't. Won't go back onto that speech. Likewise, this can be computed with an integral. So now, what's happening in that integral process? What does this expression here do? And I claim that they can think of this as a 4-step process. Step 1, the domain is sliced up into little pieces. So that interval on the x-axis we chop up into little pieces. This interval on the x-axis we chop up into little pieces. Secondly, on each piece, for whatever reason, depending on what the application is, I multiply the value of some function times the size of the piece. Now this is where you have to think about application specific. What is it that you want to multiply by delta x if you're computing mass on a tiny little piece of this rod? Well, mass per unit length. Mass per unit length is what you would multiply by length to get mass. Right, so the thing that you multiply by size, the thing that you multiply by delta x here, is mass per unit length. Okay. On the other hand, here's a different application, this area under the curve application. Once you've taken this question and sliced it up into little pieces, and of course slicing up the domain implicitly slices up the area as well. Right? So on one of these little slices of area, what would be multiplied by delta x to get the area? Well, height. So what this function is, this f, the integrand, it depends on the application you're working on. If you're computing mass, the integrand is density. If you're computing area, the integrand is height. Right? So you gotta think it through, and don't try to get in your mind that this f always has the same interpretation. It doesn't. This f depends very much on what it is that you're applying this integral construction to. Nevertheless, in all these cases, anytime you're using a Riemann sum, whatever the application is, on each piece that you've chopped up, there's some function that you're multiplying by size. Which you can see right here. There you go. The value of the function times the size of the piece. Right there in front. All right. Yeah. So, and then, it's pretty much all over at this point, except for, the details. You add it up. Right, you take a limit to make those round off errors go away. And there's your. Okay, so that's that's the idea behind the Riemann sum construction, is to break the problem down into little pieces, such that on each piece, the question at hand takes this very basic and simple structure, something times size, right? And then add and take a limit. Okay, so that's just an observation. Now, why do I want to point out, what's the strategy behind the Riemann sum? Keep in mind our goal here is not to understand single variable integrals, although that's sort of, I guess that's a first step, right? But our big goal is to generalize the idea of single variable integrals, right? We're doing multivariable calculus class. I need to define a multivariable integral. And so if I want to generalize single variable integrals, we've got to be very specific about what is it that we're going to retain and what is it that we're going to generalize. Okay, so what we're going to retain are these 4 steps in the process. We're going to, when we're defining multivariable integrals, we're going to chop up a domain into pieces, on each piece of which we're going to multiply something times size, and then we're going to add up and take a limit. Just like in a single variable Riemann sum. What we're going to change is the nature of the domain itself. Right? So here's our question now. We're going to define something called a double integral, and we'll talk about the terminology in a few minutes. Define something called a double integral. And the question is simply, what if your domain is not just an interval? What if your domain is let's say a rectangle in R2? Right, so this is a pretty big twist. I mean, we're no longer doing an integral from A to B. Where our domain was an interval on the x-axis. Now we're going to have a 2-dimensional domain. What would an integral mean in this context? And I say, well, the answer is we're going to do this process. We're going to take this domain. We're going to chop it up into little pieces. On each piece, we're going to, I'm not sure what this f function is going to be, but for whatever reason specific to the application, to be d later, we're going to multiply some function times the size of each of those little pieces. And then we're going to add them up, take a limit to make round-off errors go away, and we're going to call that an integral. Now, why would we do such a thing? What applications will this help us address? Yeah, we'll get to that. Let's not worry about that right now. Right now, I just want to talk about generalizing this construction, this Riemann sum construction here. What would be the 2-dimensional version of this? That's question number 1. So let's focus on that for the moment. And then after we've created a 2-dimensional version of this construction, then we're going to start talking about how handy it is and how useful it is for computing various different things. Okay. All right. So let's go through the process. Here is our new domain. It's a 2-dimensional domain. And step 1, chop it up into little pieces. Okay, well, how are we going to chop this up into little pieces? I guess you could chop it up different ways. What we're going to do is the old slice and dice. Yeah? Seemed like a pretty good way to take that rectangle and chop it up into little pieces. Okay. Let's talk about these little pieces. Here's one. That little piece there. Got to give that a name. How am I going to keep track of the... I can't... I'll call him Steve. Right? I got to give a name to this. That's something I can keep track of in some way. So what's a reasonable name to give to this? And I make the observation that in this process of slicing, when I sliced up the rectangle, notice I also sliced up the interval from A to B. And in the process of slicing up the interval from A to B, oh my gosh, we've already got names for all of the stuff down here. This is Math 111L. Right, this is Calc 1. So, delta x and x sub I and, the I sub interval, all that. We've got names for all that stuff. We're just going to keep them. Right? Likewise, when you do the dicing, when you slice this way, you're also effectively slicing up that interval. Let's call it the interval from C to D. That interval on the y-axis. And you can make up an analogous naming system. So we talk about delta y instead of delta x. Right? Delta x was b minus a over n. Delta y would be d minus c over n. Yeah. And you could, give these endpoints names. You don't want to use the same subscript. We use I for a subscript telling you where you are. Which of these slots are you in? Right? I goes from 1 to n. Right? So I is already due, and so I has a role already assigned to it. So what name we're going to give to the we'll keep track of where we are along here? Let's use J, let's say, instead of I. Okay, so the point is, when you're looking at one of these sub-rectangles, right, it's not a sub-interval. We use the term sub-interval because we've sliced up a big interval into, smaller intervals. Here we have a rectangle that we've sliced up into smaller, so what we're going to call sub-rectangles. Okay. So, whichever one of those things you're in, you're going to be in one of the slots on the x-axis. Let's say you're in the ith slot on the x-axis, and then likewise, you're going to be in one of these, let's say the j, one of these slots along the y-axis. Right? So if you tell me which one are you in over here and which one are you in over here, that tells me which little sub-rectangle we're talking about. So with that in mind, we're going to use the notation d sub I j. That's going to be our terminology for how to describe that little sub-rectangle. Is that cool? All right. So, by the way, what's the area of that little subrectangle? That's not a big stretch, I hope. But that subrectangle, its area is delta x times delta y. I mean, delta x is the width, delta y is the height. So that's how you compute areas. All right. By the way, going back up to our notion of Riemann sum here, note in item 2. Having chopped into pieces, we're going to be multiplying something times the size of the piece, right? What is size now? We're not looking at length. We're not looking at an interval along the x-axis with I've chopped up into little pieces that have little lengths. We're looking at an area that I've chopped into little pieces of areas that have some, how would I describe how big that little rectangle is? I would describe how big it is by its area. Right? So the notion of size changes because of the context. That has size, which is area. Okay. And everything else is just kind of following along with the pattern. On each little piece, for whatever reason, not sure what this f is going to be or what this has to do with an application. Again, we'll get to the applications later, but maybe we might have some reason at some point to multiply some function times the size, namely the area of some piece of a rectangle, after which I can then add them all up, take a limit to make the round-off errors go away. This would seem to be kind of a two-dimensional version of a Riemann sum. Again, what is this useful for? Can I still compute area under a curve? What am I going to do with this? We'll talk about that in a moment. But just following the pattern, this is a two-dimensional Riemann. Let's take a pause on that for a second. What do y'all think about that? Everybody happy? Oh, here's another thing we're going to take a pause on. How do you compute these things? Right? We'll talk about it in a few minutes. Right? There's a big worry. And you're probably all worrying, oh my gosh, we're going to have to do all those Riemann sum calculations that we did before we learned the fundamental theorem of calculus back in Calc 1 class. And I'm just going to let y'all worry about that. Okay, so notation, we call this a double integral. And that's the notation that we use. It's pretty plausible. dA, it's because it's a little piece of area. You know what I mean? why would we use two symbols there? Two integral symbols to represent that we're doing this summation like this. Well, I can give you a better answer in a few minutes. For right now, let me just say, well, it is, let's confess, a two-dimensional domain. Right? This is two-dimensional. Or if you prefer, we're adding up in two different directions. I'm not just adding along one of these sort of horizontal slices. I'm not just adding in the I direction. I'm also adding in the J direction. I don't just have in terms. I have in squared terms. Right? So it's kind of plausible that this is like an integral in two directions or something. I'll come back to that a little bit later. Another difference in notation. When you're doing single variable integrals, your domain is always an interval. And if your domain is always an interval, it's always defined by, well, what's the lower bound? What's the upper bound? Right? So this notation, integral, and then we always say from A to B, is a convenience, capitalizing on the very peculiar consistency of what intervals always look like. Intervals are always from something to something. Intervals are very simple creatures. Right? So we're no longer in that circumstance. Now we have rectangles, and they have, I guess I could write down all four of the corners or something. This seems kind of weird. Just to avoid this issue, what we do very often is just say, look, whatever your domain is, give it a name, right? And whatever the name of that thing is, just kind of make it a subscript for the double integral symbol, and that's enough. Right? And when it gets to the computation, well, again, reasonable question. But how do you compute this? Isn't that vague? Yeah, kind of. Right? And when we get to computing it, we are going to have to write it differently, and we will. But for the moment, just to express the Riemann sum that we're interested in, just having a name for the domain and defining the domain elsewhere is fine, yes. So if D is not there, is it indefinite? There's no such thing as an indefinite integral in multivariable. And I nominate indefinite integrals as one of the most unfortunate concepts in single variable calculus. Yeah, so to me, indefinite integral should just be antiderivative. Yeah, but in this context, and if you say what's a multivariable antiderivative of this function, it doesn't really make any sense. So yeah, so we're not gonna have that concept at all in single variable in multivariable. Excuse me. Sorry, whenever you see two things together, that always means double integral. Yep. There's always a domain, and if it's not written down, then the person who wrote that double integral is just being a little sloppy, arguably. But it always means double integral. Right there. Okay, so here's going to be our strategy. This is what we're going to do. We're going to see various applications. We'll see them in a couple of moments. These applications, the way we're going to get our hands on them is step one, we're going to write them as Riemann sums, by which I mean this. That's step one. And then we're going to say, oh, by the way, that's, this notation and terminology here, double integral with these little swirly, long, elongated S symbols, that's just notation and terminology to represent this Riemann sum. It's not really doing anything, it's just a label. Okay, so step one, rewrite some application as a Riemann sum, aka double integral. And then step two is how do we actually compute what we're interested in? How do we actually get a value? How do we evaluate these things? And so we'll come to that later. Right now, having defined double integrals, right? Again, we're going to punt on computing them for the moment. We'll come back to that in a minute. And I want to talk now about how do you what are these applications? What kinds of geometry problems, physics problems, whatever, can be written as double integral Riemann sums? Okay, so here's a few examples. The first one is very familiar. Now I emphasize this is an application. Right? This is not a definition. This is not an alternative definition. I don't even really like this as intuition for double integrals. I think this is inferior. as how to think about double integrals. But it's familiar. It's definitely familiar. So volume under a graph. So the very first application that you see for single variable integrals is how do you compute the area under a curve? It's something you can draw a picture of, and you can see all the participants in the Riemann sum. There they are. There's a picture, so it's nice. And this has that nice feature as well. If you have a graph, right, and you could then say, okay, well, I've got a domain down here, and sitting over this rectangle, I would like to know how much volume. There we go. How much volume is there sitting under that graph? Right? And I propose this is something you could address with a Riemann sum. Now let me write it first as a Riemann sum. Here's how you'd write it as a Riemann sum. I'm going to first say that the volume is a sum. It's a limit of a sum because, round off errors and all. But let's, how is it that this volume is a sum? Well, it's a sum of little pieces of volume that look like this. Right? If I look at one little piece of area at a time down there, and if I ask, what is the volume sitting over that sub-rectangle, that little thin slice of a slice. What's the cooking terminology for that? That's not a. What do you call it when you get these long, thin, like a shred? Like when you get the carrots in your salad and they're about that long. A sliver? Yeah. So let's go with sliver. So this little sliver of volume, right? How much volume is that? Okay, well, whatever that volume is, if I add up all of the volumes, all the little slivers that you turn this particular potato into, right? Oh, French fries. Let's go with French fries. Right? So this potato, you slice it into French fries, right? Yeah. Now I'm speaking your language. Yeah. Right. So when you slice up a potato into French fries, the total volume of the French fries is the same as the volume of the original potato. Yeah. Right. Exactly. So now, how much volume is there in that particular French fry? Well, it's going to depend on the height. Okay, well, the height is the value of z, which, because we're looking at the graph, is the value of the function. So height times area. Let's see here. Let me see if I can get that. Okay, the area down here, which for Riemann sum purposes I'll write as delta. Oh, in fact, let me even write this as delta x, delta y. Right? So you can see right here, f of x comma y times delta x, delta y, there's a French fry. Right? I'm going to add up all the volumes of all the French fries and take a limit, and that's going to give me the total volume of the original potato. Everybody happy? So that's one application right there of this construction, this two index double, this area Riemann sum, you might call it. Okay, and then having done that, let's see here, let me clean up my mess here a little bit. Okay, so having done this, I can then say, oh, by the way, there's my shorthand notation for Riemann sums, double integral. Everybody on board with that calculation so far? Now you'll notice that's not what I had written in the notes. In the notes I had a shorthand of that. In the notes I wrote hey, let's just do that. And so now this is a shorthand, right? It's a very convenient shorthand. Everybody does it. I'm all for it. But it is a shorthand. Okay? And just make sure you keep in mind when you're writing down stuff like this, just remember you are writing down a shorthand, a convenient shorthand for Riemann sums, which is what you're really doing, right? That said, it is still very convenient to do this. So this first thing that I have written down here, this just says the total volume is the sum of the little volumes that you get when you slice it up. Plausible. Right? And then the second step is, let's see here, I guess I'll do that in yellow. The volume of one particular French fry, as previously discussed, is height times area on that little, I guess I should have done that, whatever, in this particular little, sliver. Yeah. Okay, so go ahead and write it like this, for sure. It's fine. But understand, make sure to realize that that's what you're really doing. You're really writing down a Riemann sum and then saying, oh, there's my convenient shorthand notation for the Riemann sum. Okay, so I'm going to do this shortcut then because it's just so much easier. Okay. All right, so that said, we have one application under our belt. Here's another application. Suppose I want to compute the mass, not of a one-dimensional rod. Suppose I want to compute the mass of a two-dimensional region like this. And maybe the density is not constant, so maybe it's it's more dense down over here in this bottom left-hand corner. All right, so the density varies, and not in some convenient way where you could just slice it, and on one of the full long slices the density is like constant or something. Wouldn't that be nice? That'd be a very Calc 2 kind of a question. But so the density varies in all different directions in a lumpy and wiggly sort of a way. So how do you deal with that? How do you add up all of these masses? And the answer is you slice it up into little pieces, slicing in both directions. On each little piece, well, look, the areas, the density is very different over here. But on this little tiny little piece, on that little itty bitty little area, the density is it's pretty much constant. And so on that little piece, mass is approximately density times area. And if mass is approximately density times area, adding up all the pieces of mass is the same as adding up these expressions that are density times area. And notice I end up with a double integral. Everybody on board? Okay. Suppose I want to compute the population of, either Wyoming or Colorado. That's what we're confined to at this point because we're stuck on rectangles. That's all we have is rectangles. We'll talk about how to do other states later. Right? The non-rectangular states is different. But for the moment, suppose I want to compute this population. How many people live in this region here, this rectangular region? Well, if I know the population density, well, that's nice and all, but the population density might not be, conveniently distributed. It might be varying in both different directions. So again, what do? Well, what you do is you argue one little piece at a time. In that little piece, you can talk about population density. Population is going to be some function, people per unit area times area. And again, add that up over all the pieces, and you get the total population. Okay, so lots of different applications, and this is just a couple that, we've seen very quickly. Okay. So now let's go back to our strategy here. We've seen that there's lots of applications that I can rewrite as Riemann sums. Now I want to focus on the other side. How do I actually compute and get these down to a numerical answer? Yeah.
For the is the function like density or essentially?
Yeah, so you're talking about this P of X comma Y?
And then
that's population per unit area. So the units are going to be like, people per square mile, or people per square, whatever, square kilometer. Does that make sense? Yeah. All right, and so let me remind you, your integrand always depends on your application. If you're computing population, then it's, people per square mile. If you're computing the number of mosquitoes, right, then it'll be mosquitoes per square mile, or whatever. If this is a sheet cake, and you want to know the total number of calories in the sheet cake, then it's calories per square inch. Right? Yeah, let's not do that. Yeah, that's right. Yeah, disturbing calculation. Yeah. Right. Okay. So how do you compute though? How do you compute these things? And look, at proper treatment of the calculation I'm going to show you is a little bit beyond Math 212, and it's highly algebraic. And I think it's much more satisfying to do this little trick I'm going to pull, which is to consider one of these applications. And I'm going to just consider the volume question here for the moment. Just the volume. Right? And let's compute that volume a different way. And I bring you back to your Calc 2 class where you remember you computed volumes of rotation. You take some curve and you rotate around the x-axis and you get a sideways vase of some sort. And then you slice it, and you can talk about, on each slice, you can talk about the area times the thickness. Everybody remembers how those go, right? Okay. So you can do the same thing here, actually. It's just that they're not rotationally symmetric. And so you could say, look, going in the y direction, that cross-sectional area, now let's pretend that I know what that cross-sectional area is. But look, if I do cross-sectional area times the thickness of a slice that I might make, right? There's a slice of some sort of thickness that I might make. Area times thickness gives you the volume of that little slice, and I add all those up from C to D, and it gives you the total volume. So just like in a volume of rotation problem, it's just this is not a volume that happened to come from a rotation. Okay. Right, which is all well and good except for the fact that we don't know what that is. In a volume of rotation problem, this was the area of a circle, or worst case, area of a washer, right? Annulus. And so pi r squared, or pi r2 squared minus pi r1 squared, whatever. In this case, not so lucky, but it's not that bad to figure out what that area is. That area, I will observe, is the area under a certain curve. Right? It's the curve that you get when you take that cross-section of the surface. And we know how to compute the area under a curve. The area under the curve is an integral itself. Let's think about that integral. I mean, what is this? What is height as a function of? By the way, what's my variable for this integral? For this integral, you'll notice that I'm going kind of that way, right? I'm looking at slices that are going in the x direction, so the thickness is going to be dx. The height, let's see here, I'll do this in yellow. The height, that height depends on, well, it depends on x. Right, and I've already agreed that I'm doing an integral dx because, x is what has to range over various different values. So this is an x integral. X is the variable. F is the height, but f of x comma what? Well, it's f of x comma, well, whatever your y is, right? I'm trying to compute the area at a particular value of y. The value of y, that where you're trying to compute the cross-sectional area, that's constant for the purposes of this second calculation. When you're trying to figure out that cross-sectional area for a given value of y, that means y is constant. So for this whole entire process, y is constant. We treat it as a constant. So this is called a partial integral. Kind of like a partial derivative. You remember partial derivatives, you treat all the variables constant except for one. Here we're treating all the variables constant. We're treating y as a constant, except and then put not the x there. Okay. So what we end up with, and this is kind of a clever observation. It takes a certain amount of audacity to proceed with this calculation, because it'd be real tempting from a single variable calculus point of view to say, well, I guess I can compute that volume as an integral of cross-sectional area, but this area is not something familiar, so, oh well, I guess that didn't work. Right? It'd be very easy to bail, but it, if you just press on and realize that area is computable as an integral, then notice what we have is an integral that is inside of another integral, which is a little creepy the first time you think about it, right? So here you go. So we compute that volume as an integral of an integral, and don't forget the inside integral is what represents cross-sectional area. Okay, so right, so why do we need double integrals in the first place? Right? If we can compute these volumes with a single variable integral of a single variable integral, why do we need this construction? I'll come back to that in a couple. What I want to do here is notice that, well, look, if I computed volume with that formula, and if volume is also equal to this, then the appeal that I want to make to y'all is that means that that's equal to that. And this turns out to be the more valuable observation here. That's, I think, these greater issues that I'm going to sweep under. We don't need to be worried about. But what we really need to make use of is the fact, not that this is a formula for computing volume. It's useful sometimes, but the fact that this is a formula for computing double integrals is the real win here. Right? So if you ever find yourself with a double integral, you can rewrite it as what we call an iterated integral, because this is an integral inside of another integral. If it was me, I'd call them nested integrals, but iterated suggests you're doing something and then doing it again, which again, my quibble is that, well, these aren't the same. Here we're doing an x integral, and then subsequently we're doing a y integral. They're not really the same thing. Anyway, but the more common, by far, terminology is iterated integral. All right. Okay, so let's put it all together then, and let's actually solve our first application. I've got a mass distributed over some sheet, some two-dimensional region. The sheet in question has this range of values for x, that range of values for y, so this is a rectangular sheet, right? And the mass per unit area, so the density in this context, is given by this function here. And the question is, what's the total mass on that sheet? Okay, 3-step process. Let's go back to our little roadmap here. Anyway, 3-step process. Step 1, old news. I've already argued that mass is a double integral of density. And, this is a typo. I apologize. That's supposed to be density. Sorry about that. Mass is double integral of density. Previously discussed. Second, we just got through arguing that double integral can be rewritten as an iterated integral. Right, so there's that. Note the bounds on this iterated integral. X goes from 1 to 3. And y goes from 2 to 4. Make sure to get those right. And by the way, they pair up like this, right? Not like that. You guys see what I'm talking about? This is not optional. And this absolutely got to be that way. So the inside has to match to the inside and the outside to the outside. Periodically, I'll see students do it the other way. Unacceptable. It's really not okay because it communicates a different thing. Okay, so please do be careful with that. Okay, so step 1, application to a double integral. Step 2, double integral to an iterated integral. And now step 3 is just compute. And this is single variable calculus at this point. There's a single variable calculus problem squeezed inside of another single variable calculus problem. But it is, in fact, just single variable calculus. So let's walk through this real quick. Let's focus at first on the inside integral, which, by the way, we have to, right? There's a temptation to say, well, I want to do the outside one first. Well, the outside integral has an integrand that is this thing I have circled in blue, and I don't know what that is yet. So you can't take an antiderivative of something if you don't know what it is yet. So you can't. You got to go inside out. Okay, so that inside integral. Notice it's an integral with respect to y. That means y is the variable. That means x is to be treated as a constant. So the first thing I want to point out, right, because x is a constant, the antiderivative with respect to y is just constant times y. So it's kind of like with partial derivatives, and partial derivatives are great, and they're even better than regular single variable derivatives because you get to pretend that stuff is constant, which is awfully handy, right? And likewise here, when you're doing an integral, an inside integral, make note of what is your variable, and everything else is constant. Okay. All right. So let's see, so that's a constant. Well, what is the antiderivative, though, with respect to y of y squared? Well, 1/3 y cubed, right? That's a Calc 1 observation. 2 to 4. My little superstition, by the way, is I always write y equals 2 to y equals 4, because notice what I'm going to do with the 2 and the 4. I'm going to be plugging them in over here. Plugging them in for what? You'd be surprised how easy it is to take that y equals 2. If you just have it written down as 2, to inadvertently plug it in for the x's, either in addition to or instead of the y's. So I urge you to follow my own little superstition on this. You write y equals 2, and that's a great reminder to only plug that in for y. The x's stay x's because they're constant for the purposes of that inside integral. Yeah? Everybody see what I'm saying there? Cool. Okay, so you plug these in and subtract a little bit of algebra. I'll let you guys do that algebra. What it comes down to is 2x squared plus 20, which is a function of x, which is a little unsettling because wait a minute, when I use the fundamental theorem, aren't I supposed to get a number? Well, I did. This is constant for the purposes of that inside integral because x is a constant. Right, so for a given value of x, this is the value of that integral. All right, now on to the next step. This outside integral. For the purposes of that outside integral, now x is a variable. And so, I do in fact have, as seen from the outside integral, I have a function. And so this really is just, no kidding, Calc 1 problem. And so, boom, numerical answer. Let y'all work out those details. Make sure you can do that, by the way. This is one of many opportunities when it's going to occur to me to remind y'all that Calc 2 is a prerequisite for this course, and you've got to make sure that you're good with all that Calc 2 stuff. Now, the good news, we're not going to use like inverse hyperbolic cosecant integrals and that kind of super wacky stuff. But make sure you can do, basic integrals, of course, right? Substitutions, integration by parts. I personally am a big believer in trig substitutions, right? So make sure you can do all those things because on the exams and on the final exam, it's going to be assumed that you're good with all those things. Okay, so now let's go back to an earlier question I asked. If I can do this, what's the point of that? Why don't we just jettison double integrals after all? It turns out that this, the audacity of pressing forward with this single variable integral of a single variable integral, my gosh, didn't that just rock? Isn't that what allowed me to actually compute this in the first place? So why are we messing around with a brand new kind of Riemann sum, double integrals? And this is a very important question to address. And the answer you can see in this example. And it's because if I were to take out that double integral and just try to go straight from there to there, it's not clear how I would make that case. How would I make the case that mass can be computed as an integral of an integral of density. And you might be thinking, didn't we just do that? Right? But we didn't. We did that argument for volume. Volume is a very specific and particularly convenient object because volume relates to this, what I like to call intermediate concept of area. And I could say, yeah, area times thickness gives me volume. Well, I mean, having this pre-existing geometric notion of area is essential then to this process. What's the mass version of that? There isn't really one, right? So when you try to make sense out of, okay, in this context here, what does this mean? What is, x squared plus y squared is mass per unit area, and I'm multiplying that times length. That's not a thing, right? So I can't argue. I can't just say, oh yeah, well this, whatever that thing is, that's the thing that you multiply by length to get mass. It's not a pre-existing notion, so you can't make the argument. So we have to, step one, argue that it's a double integral, because there I'm multiplying mass per unit area times area. That's something that makes sense, right? People per square mile times square miles gives you people. Not like sliced up slivers of people. It's disturbing, right? It doesn't make any sense. It's not something we can really work with. So in order to get your foot in the door at all, you have to have double integral. And then having done so, yeah, of course, so you want to convert that into an iterated integral so that you can compute. So here's what our roadmap is going to be. This is the modified double integral roadmap. Step one, turn your application into a Riemann sum, aka double integral. Step two, rewrite your double integral as an iterated integral. And step three, compute your iterated integral with the fundamental theorem of calculus twice. One after the other, and that'll give you your answer. Yep.
When you were doing the example, how did you know when you were doing the iterated integral, but the integral y?
How to do it this way instead of that way?
Yeah.
It doesn't matter. You can take your choice.
Okay.
Yeah, and so here's a good exercise. Technically, all I did in this argument here is I proved that you can do dx, dy. There is a very similar looking argument that you can write down and draw similar but significantly different pictures that argues that you can do it the other way. So give that a shot. I mean, in other words, feel free to cheat off of this, right? But it'd be sort of switched to just have the x and y play analogous roles, and you'd get exactly what you would expect. Okay. Yep. Yes.
Are there triple integrals?
There are. Yeah. And that's a topic for another day, unfortunately. Yeah.
Another day in this class.
Sorry?
Another day in this class?
Yeah. Oh yeah. Yeah. And so it's I mean, yeah, we'll talk about it later, but yes.
So this like computation is best with volume.
Well, no. This computation works with anything that I can turn into a double integral. Because I can always turn double integrals into iterated integrals, and I can always compute iterated integrals with old techniques. So this works for any one of these applications here. Volume, mass, population. The point is, you have to be able to, step one, turn your application into a double integral. Anything that you can turn into a double integral, you're good, because you can always turn double integrals into iterated integrals. What you can't do is immediately turn a population question, just, bypass that and go directly into a single variable integral of a single variable integral. That does not make any sense.
So all the questions need that intermediate every single.
Yeah, if you're gonna, I suppose, with the exception of volume, but there's no point in making the exception, right? So let's say any double integral you're going to do in math 12, you've got to write down the double integral, because that's the only meaningful first step you can take, and then you can rewrite the double integral as an iterated integral. Yeah. Okay. So let's see here. Let me take stock of where I am. Oh, and I am out of time, aren't I? Man. Okay. So we are falling increasingly far behind. I'm not sure exactly what to do about that. So I'm thinking about solving the problem by doing a catch-up video lecture. Where I just have y'all, watch a recording of me talking about math, and then we won't be a lecture and a half behind anymore, as we are now. So anyway, I'm not quite ready to pull the trigger on that, but we might do that at some point, so be prepared for that at some point. Okay, all right. Stick around for a moment. Let me pass back exams.